Hey guys, welcome to yet another video by Scalar, and in this particular video we're going to look into bit manipulation. So before we move on to this particular session, please make sure you subscribe to our channel so that you don't miss our upcoming videos, and also leave a like if you enjoy our content. And if you have any queries, please leave a comment down below and we would respond to you and make you understand whatever query that is. So now before we move on, let's understand a little bit about bit manipulation. So bit manipulation is basically an act of algorithmically manipulating your bits. So bits, basically in a byte you have 8 bits, so you're manipulating every single bit for doing some particular action. For example, the most popular tasks in computer programming which needs bit manipulation are encryption algorithms, data compression, correction algorithms, optimization, and more. So these are the things which you can do with bit manipulation, and a good software engineer should also be aware of bit manipulation. So that's what is going to be covered in this particular session. Without any further delays, let's begin with it.
Let's talk about bit manipulation and understand its importance for an engineer like you. Bitwise operators are very fast. If you understand how various data types are stored in memory, you will be able to solve very hard problems quite optimally. Good understanding of bit manipulation enables you to optimize for space as well as the execution time of the program. Now, speaking from an interview perspective, there are chances that in product company interviews you will be asked direct or indirect questions based on bit manipulation. An example of direct question would be to divide two numbers A and B without using division, multiplication, or the mod operator. Now, an indirect question would be to design a system which alerts a user whenever he visits a malicious website. You can be asked to implement this feature for a browser like Google Chrome or Firefox. There are many ways to do this, but the best way to do this is using a Bloom filter which contains the logic of bit manipulation again.
Good evening, everyone. Am I audible? Am I audible to everyone? If I'm audible, can you guys give a thumbs up? Cool. So, guys, first of all, before we start the class, everyone please congratulate Savita Nandan. Savita is the winner of the last contest. Okay, Savita, if you are here, someone from the Scalar team will be reaching out to you for the t-shirt. Okay. So similarly, guys, today also we are going to have an assignment, and the person who solves all the problems of that assignments in the lowest time gets a t-shirt. Okay. Cool. So today we are going to study bit manipulation. Okay. Do you guys understand what is empathy? Right. Empathy is a very, very important quality that every one of us need to have. Right. Right. So if you win the contest, you will be getting the exact same T-shirt which I am wearing. Right. So if you have empathy, if you know, if you are able to feel how the other person is feeling, or how if you are able to look from the other person's perspective, then you can resolve very serious issues in your relationship, right? Similarly, if you are able to see how a computer thinks, how a computer perceives number, then you will be able to solve very, very complex problem in a very optimal way. Okay. Now, if from our perspective, we see numbers like 4, 5, 25, 100, etc. Right? We see numbers in decimal, but computer doesn't see the numbers like this. Computer sees the numbers in binary. So for computer, this is not 4. This has to be 100. For computer, this is not 5. This has to be 101. So everything for computer is binary. Okay. Now, if you are able to understand how computer stores these numbers and how computer actually performs operations on these numbers and what are some of the basic bit operators, then you can solve very complex problems very easily. Okay. Before actually jumping onto the problems, we'll quickly revise some of the basic bitwise operators. Okay. So I hope you guys, after yesterday's class, you guys have read about the basic bit operators, right? So we'll be talking about AND, bitwise AND, we'll be talking about the bitwise OR and the bitwise XOR. Okay. How does bitwise AND function? So everyone must have studied this in the school, right? So bitwise and before we see how these functions, let us define a terminology which is a set bit and an unset bit. So any bit which is having a value 1 will be called set bit in our context, and any bit which has a value 0 will be called unset bit. Okay. So if I ask you how many set bits are there in the binary representation of 4, the answer is 1, because there is exactly one set bit. How many unset bit are there in the binary representation of 5? There is exactly one unset bit. Okay? So this is the basic, these are the basic terms which we will be using again and again. Okay. So how does the bitwise AND functions? The bitwise AND always returns a set bit if both the operands are set, right? So if you have 1 and 1, this is the only case when your bitwise AND is going to return a set bit. For all the other possible operands, you will be having a unset bit in the return. Okay, so all of these, if any of the operand is an unset bit, you get a unset bit in the answer. If both of the operands are set, then only you get a set bit in the answer. Now the OR is exactly opposite of it. So OR will give a set bit if any one of the operand is a set bit. For example, if you have 1 or 1, or if you have 1 or 0, or if you have 0 or 1, for all of these you will be getting a set bit. If both of the operands are 0, then only you will be getting a unset bit. Okay. How does XOR functions? So XOR is a very interesting operator, right? So XOR says that if both the bits are having the exact same value, if both the operands are having the same value, then it is going to return an unset bit. So if both the operands are, let's say, set bits, or if both the operands are unset, in both the cases we will be getting an unset bit. XOR only gives a set bit if the two operands are different. So if we have 1 XOR 0 or 0 XOR 1, in this case we'll be getting a set bit. Okay. These are the basic bitwise operators. Okay, now I just said that XOR is a very interesting operator. Why is it interesting? Because this property that the XOR of exact same bits is always going to be 0. This makes XOR interesting. Okay, let us try to analyze this. If I have an integer a, okay, and if I take the XOR of this integer with 0, what is the result that I should be getting? Okay, before actually jumping to this, let us try to understand how to take how bitwise operators functions for integers, right? So let us remove this. We'll come back to this again. If I have to take let's say 4 and 5. So till now what we have seen is both the operands were single bits, right? Now we have numbers which are not binary numbers. How is it going to work? Similarly, if I have to take 4 or 5 and 4 or 5, how are all of them going to work? So to get the answer of this thing, you will first convert the number to its binary representation. So 4 can be represented as 100, 5 can be represented as 101. And now since you are taking AND will give you a set bit only if both the bits are set. For any other cases, it is going to give you a unset bit. So you will get 100. What is the decimal representation of 100? Decimal representation of 100 is 4. So 4 and 5 is nothing but 4. Okay. Similarly, if I have to calculate 4 or 5, again, I will just convert this to binary, and similarly convert 5 to binary as well, and then we do the bitwise OR. Okay, so now here we can see that this is going to be 1 because 1 or 1 is 1. 0 or 1 is also 1. So both of these two are going to return a set bit. 0 or 0 is 0. So what we do is we convert them, we convert both of the numbers in their binary representation, and then we do the bitwise, whichever operator is it, right? So if you are taking the bitwise OR of two numbers, you will just convert them to binary representation, and then for all the corresponding bit pairs, you will be doing this operation. Okay. Similarly, if we have to, so this is going to be 5. Okay. If you have to take what is 4 XOR 5, so 4 is again 100, 5 is 101. Now this is interesting. Can you guys quickly tell me the answer? XOR gives you a set bit only if both the bits are different. So there is only one pair where both the bits are different. Here we have 0 and 0. Here we have 1 and 1, right? So this is going to be 0, 0, 1, which is nothing but 1 in decimal. Okay. Cool. So this is how we will be taking the bitwise AND or XOR of integers. Okay. Now tell me one thing. If I tell you that a is an integer and you have to calculate the XOR of a with 0, what should be the answer? Should 0 be the answer? XOR of a with 0. Correct. The XOR of a with 0 is going to be exactly equal to a. Why is it going to be exactly equal to a? Let us assume that a is in binary representation. A is represented by this random binary string. Okay, and then in the second, as a second operand, we have 0. Right. So 0 is going to have zeros or unset bits in all the bit positions. Now, when you do a bitwise XOR between these two numbers, you can see that for all the digits, for all the bit places where a is having a set bit, 0 is definitely going to have a 0. So for all of them, you will definitely get a 1, right? So for all the bit position where a is having a set bit, the answer also has a set bit. And for all the bit position where a has a 0, 0 also has a 0. So both of them are same. So the answer will also be 0. So this is nothing but this is exactly same as a. So a XOR 0 is going to be equal to a. Okay. Now if I ask you that what if I take the XOR of a with a itself, what should be the answer? XOR of a with a. Again, let us try to represent a in binary form. So let us say that a is a number which can be represented by this random binary string, and the second operand is exactly the same value because the second operand is also a, right? So for any position where the first a has a set bit, the second a is also going to have a set bit. For any position where the first a has a non-set bit, the second a is also going to have a non-set bit, right? So the XOR of same bits is always going to be 0. So in all the bit positions, we'll be getting a non-set bit, which is equivalent to having a 0 in decimal, right? So XOR of a with a is 0. These two are very, very important properties of XOR, which will actually allow you to solve very complex looking problems in very optimal way. Okay. Okay, now let us see one more property of XOR. If I say that there are two integers a and b, okay, and a XOR b is equal to k, what can I say about the value of b XOR k? If a XOR b is equal to k, can I predict what is the value of b XOR k? Okay, I think there is a big lag in what I'm writing and what I'm saying, right? So I will quickly reshare my screen. Just give me a moment. Till then, you can just figure out what is the answer here. So if a XOR b is equal to k, then what should be the value of b XOR k? So if a XOR b is equal to k, what if I take the XOR of a both sides? If or let's say, what if I take the XOR of b both side? If I take the XOR of b both side in this equation, this is going to be a XOR b is equal to k XOR b, right? Now, what can I say about this equation? A XOR b XOR b, right? So b XOR b, these two are exactly the same. So these two will cancel out each other, right? We have just seen that a XOR a is going to be 0. So similarly, b XOR b is also going to be 0. If this is 0, I will be getting a XOR 0 equals to k XOR b. What is a XOR 0? We have just seen a XOR 0 is nothing but a. So a is equal to k XOR b. So we can say that b XOR k is nothing but it is equal to a. Okay. Does this make sense to everyone? Similarly, you can take a XOR of a both side, and you can also prove that a XOR k is going to be equal to b. Okay. Now these are some of the basic bit operators and some interesting facts about them. Now there are two more bit operators which are not that basic, but they are also very interesting. Okay. So there is an operation which is represented by this sign. Okay. And this is called the left shift operator. And similarly, the counterpart of this operator is this, which is called the right shift. Okay. What do we mean by left shift? So left shift means nothing but you are shifting the bit positions. You are shifting all the values which are there in the bits towards left side. Okay. So for example, if I have 1 and I left shift 1 by 1 bit, if I have to left shift 1 by 1 bit, what how will I write it? I will write it something like this. So I am left shifting 1 by 1 bit. Okay. So I'm left shifting this number by these many bits. Okay. So how is it going to work? So let us say that the computer that we are using is representing all the numbers using 5 bits. Okay. So if I left shift 1 by 1 position, what will happen is all the bits will be shifted towards the left side by 1 place. So this 1 will come here, this 0 will come here, this 0 will come here, this 0 will come here, and this 0 will be removed from this equation. So this 0 is gone, and here in this empty position a new 0 will be added. Okay. So what is the end result that we are getting? The end result is nothing but 10, which is nothing but equal to 2 in decimal representation. Okay. If we further left shift this by one position, then what will happen? If I further left shift this, I will get 0 here. This one moves here. This 0 moves here. This 0 moves here. This 0 is removed from this, and here we get a new 0. In the last position, we'll be getting a new 0. Okay. Now what is this? What is this number? This is nothing but 4 in the decimal representation. Okay. Similarly, let us try to do it once again. If you again left shift this number by 0, you get 0 here, you get 0 here, you get 1 here, this 0 here, this 0 is removed, and you add a new 0 in the left corner. What is this number? This number is nothing but 8. Right? So you can quickly observe that whenever you are shifting a number, you are doing a left shift on a number by 1 bit position, you are doing nothing but you are just multiplying that number by 2. So 1, initially you had 1, then you get 2, then you get 4, then you get 8, right? And in the next operation, you will be getting a 1 here, and then all zeros here. This is nothing but 16, right? So whenever you are doing a left shift by 1 bit position, you are always multiplying the number by 2. Okay. Now similarly, the right shift is the counter part of this operation. So what you have to do in right shift is that you will be shifting all the bits to right side, all the bits by the specified number of positions toward right side. So for example, if we are starting from 16, okay, if you are starting from 16 and you are doing 16 right shifted by 1 bit, what will happen? All these bits will be shifted towards right by 1 bit. So 1 comes here, 0 comes here, this 0 comes here, and then this 0 comes here. This 0 is gone, and in the left end you will be appending a 0. Okay, so what is this number? This number is nothing but 8. So initially you had 16, now you have 8. Right? In the next iteration, what will happen is this 1 will come here, this 0 comes here, this 0 comes here, and this 0 is removed, and again you will be inserting a new 0 in the left end. What is this? This is nothing but 4. So now you can see that you are always dividing by 2, right? So left shift is equivalent to multiplying the number by 2. Right shift is equivalent to dividing the number by 2. If let's say I do a right shift of 1 by 1 bit position, what will be the answer? Right shift of 1 by 1 bit position. So if my 1 is represented like this and I am right shifting it, so this 0 comes here, this 0 comes here, this 1 is removed, right? And this 0 comes here. Okay, and in the left corner we add a 0. So the answer that we get is 0. So even if you have a set bit here, that will be removed. Okay. Cool. Now let us try to solve an easy problem. Okay. What if you are given a number and you have to check whether the ith bit of that number is set or not? Given an integer, and this is going to be a positive integer, check if the ith bit of the integer is set or unset. Okay, so how can we solve this problem? If you are given a number n and you have to check whether the ith bit is set or not. What about negations? Negations, if you have a bit which is representing the negation sign, that will not be removed in a logical shift operator. So even if you are shifting a number which is negative, the result that you get is also negative. Okay. So how are we going to solve this problem? So let us say that the number that is given to us is 6. Okay, and we have to check whether the second bit is set or not. Okay, so what is 6 in binary? 6 in binary is nothing but 110. What is the second bit? Second bit is this bit, and I have to check whether this bit is set or not. How can we do it? So we have seen all the basic bit operators, right? And now there is a bit operator which is bitwise AND, which only returns a set bit if both the operands are set, right? So in my opinion, this can be a very good candidate to analyze whether we have a set bit at any given position or not, right? So if, let us say, I construct a number where we have a set bit at this position but unset bits in all the other positions, and I take an AND of this number with the given number, okay, can I say that if the result is non-zero, then we will always we can say that this bit is set, or if the result is 0, we can say that this bit is non-set, right? Because if the result is non-zero, which in this case is which is the case in this question, the result will only be non-zero if this bit is set, right? Because we are making sure that in the number that we are constructing, the ith bit is set, right? And all the other bits are unset. So if we are taking an AND of this number with the given number and the answer is greater than 0, then we can say that yes, the ith bit is set. Okay. If the answer is not greater than 0, in that case, what will happen? Since all the other bits of this number are unset, and this position is also giving a 0 in the answer, that means that the original number had a unset bit at that position. Is this thing clear to everyone? So we just have to construct a number which has a 1 at the ith bit, and all other bit positions should have a 0, right? How can we construct such a number? So we know that to construct this type of a number, we just have to shift. If I have 1 already, right? This is how we can represent 1. Now if I just left shift 1 by ith position, right? So if, let's say, I have to check whether the third bit position is set or not, right? So I can just do 1 left shifted by 3. So 1 left shifted by 3 is going to be 2 raised to power 3, right? Sorry, 2 raised to power 2. So we can say that right, sorry, one left shifted by, we'll be doing here 1 left shifted by 2, right? So 1 left shifted by 2 is going to be 2 raised to power 2, which is 4. And now you can take the XOR, you can take the AND of this constructed number with the given number. If the result is greater than 0, then you can say that yes, the number has a set bit. So what will be final equation? You will just have to return if your number and the bitwise AND with 1 left shifted by I bits. Okay, if this is greater than 0, then you return true, else you return false. Okay, this is how you can check whether the ith bit in your number is set or not. Okay, now there can be other ways as well, because this number is nothing but 2 raised to power I, right? So you can also calculate 2 raised to power I, and then that can also be used, but this is going to be more optimized. Okay, can we use other bit operators as well? Yes, you can definitely use, but this is the easiest thing. Based on the properties of other bit operators, you can also figure out a different way to figure out the same thing. Okay, let us see another quick question. If you are given an array, find the XOR of all the numbers where ith bit is set. Now, given that you are able to find whether the ith bit of a number is set or not, can you also find the XOR of all the numbers in a given array which has the ith bit, which has a set ith bit? So you are given given an array which is an unsorted array of positive integers. Okay, you have to find the XOR of all the numbers, the collective XOR of all the numbers where the ith bit is set. Okay, so if let's say I is equal to 1, so you just have to check whether you just have to calculate the XOR of all the numbers which have a set first bit, right? So for example, 2 does not have a set first bit because 2 is 1 0. 4 also does not have. 10 also does not have. 1 has a first set bit. 3 also has a set bit. So the answer that you will be returning is going to be the answer of 1 XOR 3. Okay. Now can you guys, you just have to apply a loop, and for every number you check this thing. If this condition satisfies, then you calculate the XOR of that number in a cumulative XOR sum. Okay. So will you be able to write the code for this? Should we move to the next problem? Correct. Cool. Now let us see a very commonly asked problem, okay, which is very common in interviews. Okay, the question says that you're given an array and you're also given the condition that in this array all the numbers appear even number of times except one. Okay, so there in this given array all the numbers are occurring even number of times. They can occur 2 times, 4 times, 6 times, 8 times, and so on. But there is exactly one number which occurs odd number of times. Okay, so for example, if your array can be 2 1 3 2 1 1 1 4 4. Okay, so now in this array you can see that 2 is occurring twice, 1 is occurring 4 times, 4 is occurring twice, but there is exactly one number 3 which is occurring once. So there is exactly one number which will occur odd number of times, and all the other numbers will occur even number of times. You have to return the number which is occurring odd number of times. XOR of all the elements. Okay, so I can see that most of you are giving the correct approach, which is XOR of all the elements, which is absolutely correct, right? So we know that A XOR A is 0. We have seen this. Now, if A XOR A is 0, what will be the value of A XOR B XOR B? This will also be 0 because B and B will also cancel out each other. A and A will cancel out each other. So this will also be 0. What will be the value of A XOR B XOR A XOR B? Again, this is also going to be 0 because when you are calculating the XOR, order does not matter, right? You can calculate the XOR in any order. You can calculate the XOR of A and B or B and A. Both of them are same thing. So this is also going to be 0. Now, if you just add a C in between, what will be the answer now? The answer now is going to be C because A and A cancels out, B and B cancels out. So only C is remaining. So if all the numbers are occurring even number of times and you take the XOR of all of them, they all will be reduced to 0. The only number which is occurring odd number of times, let us consider that also. So if let's say that there is a number x which is occurring odd number of times, right? So if this is the case, if the number is occurring 3 times, then what will happen? These two x will cancel out each other, and you will be remaining with exactly one x, and the XOR with 0. This is nothing but equal to x. Doesn't matter how many times the x is occurring, but if it is occurring odd number of times, all the even occurrences will cancel out each other. They all will become 0, and at the end you will be remaining with one odd x, right? So the answer is always going to be x. So if you quickly take the XOR of all these numbers, then you get the element which is occurring odd number of times. Okay, is this thing clear to everyone? If you have to just quickly write the code for this, this is going to be a single line, a single for loop code. You can just initialize an answer with 0. Now you can say for I equals to 0, I less than n, I plus plus, answer equals to answer XOR a of I. And this is it. Here you return the answer. Okay. Okay, now let us see another very similar question, but a very difficult, supposed to be difficult question. Okay, let us say that you have a similar type of array where all the numbers are repeating even number of times except two numbers. Right, so initially there was exactly one number which was appearing odd number of times, right? In this case, there are two numbers which are appearing odd number of times. All the other numbers are appearing even number of times. Okay, and you have to return both the odd occurring numbers. Okay, so for example, if the array is 4, 1, 2, 3, 5, 4, right? Now in this case, you can see that 4 is occurring even number of times, 1 is occurring even number of times, 2 is also occurring even number of times, but 3 and 5 are occurring odd number of times. Okay, so in this case, you have to return both these elements. Is the problem clear, guys? Now the suggestion is, can we use mapping? Yes, you can definitely use mapping. If you use mapping, what will be the time complexity? What will be the space complexity? Varun is suggesting from XOR of all the numbers, we can construct the two numbers. How? Varun, can you quickly write down your approach? Okay, now another suggestion is that we can quickly take the XOR of all the numbers. That will give us A or B, and using this we can construct A and B. Okay, uh, just try for that. If can you construct two numbers out of their XOR result? Dipanshu, that is absolutely correct. That is in the correct direction. Okay, let us see all the approaches one by one, right? So one of the approach that some of you have sent is that sort the numbers. Okay, if I sort the numbers, what will I get? I will get all these numbers in sorted order. If all the numbers are sorted, can I say that all the numbers which are appearing even number of time will always appear together in the sorted array? Since the values are same, the pairs are always going to appear together, right? So once the array is sorted, you can quickly count the occurrences of each and every element, right? So if you start from here, you see that this is 1, and let us see how many ones are there. So once you reach to 2, you can see that there are 2 ones, so 1 is not the answer. Then you see for 2, then you do the same thing for 3, and then you can say that 3 is one of the answer, and so on, right? If you do this, what is going to be the time complexity? If you sort the arrays and then count the occurrences of each and every element, sorting, the most optimized sorting algorithm that we have studied is quick sort or merge sort, right? Both of them run in order and log n in the best case, right? So if you are sorting these numbers and then you are finding out the answer, the time complexity is going to be order n log n. The other approach that was suggested is that use a hash map. So we'll create a hash map. This hash map is going to have the array number or the value along with the frequency, right? So what we are suggesting is that you will iterate over this original array and you will maintain the frequency of all the elements in the hash map. Okay, cool. So whenever you are maintaining the frequency of all the numbers in the hash map, once all the frequencies have been calculated, now you can again reiterate over the hash map and check which is the number that is having a odd number of occurrences, right? Yes, hash map or dictionary in Python, right? The same thing. Okay, so in this case, you will be having 4, 1, 2, 3, and 5 as the keys, and the values are going to be 2, 2, 2, 1, 1. So then once all the frequencies are calculated, you can quickly iterate over this hash map and you can figure out that these two are the numbers which are appearing odd numbers of time. If you use a hash map, what is going to be the time complexity? You are doing one iteration to calculate the frequencies, right? In one iteration, you count the number of times each number is occurring, right? So that is going to cost order n. And then once the hash map is prepared, you do another iteration over the hash map and check which are the numbers which are occurring odd number of times, right? So that is also going to be order n. So effectively, it is going to be order n. What is going to be the space complexity here? If you are using hash map, definitely you are using some extra space of order n complexity, right? So if you are using hash map, you have reduced the time complexity from log n to order n, but you have also increased the space that you are using. Okay, we have to solve this problem in order n time complexity without using any space, which means order 1 space complexity. Okay, cool. So this means that we can definitely not use a hash map, right? So what can we use? Let us go back to the previous problem. In the previous problem was also very similar, right? So if we take XOR of all the numbers, in the previous problem we were directly getting the answer. In this problem, what do we get? If you take XOR of all these numbers, right? Let us quickly take the XOR of all the numbers. We have 4, 1, 2, 3, 2, 1, 5, 4. If we take XOR of all these numbers, what do we get? 4 and 4 cancels out each other. 1 and 1 cancels out. Then you have 2 and 2 cancels out each other. So in the answer, you will be getting 3 XOR 5. Okay. What is 3 XOR 5? 3 is this, 5 is this. So you will be getting this as 0, 1, and 1. Right. So you will be getting a 6. Now, how does a 6 help you out in figuring out that the two numbers are 3 and 5? Can you construct 3 and 5 from this 6? No, right? There are multiple possibilities because you know that in 6, this digit is a set digit. Now, a set digit can come from two combinations, right? Either you can have 1 0 here or you can also have 0 1. Both of them are going to give you a set bit. So this is very hard to actually construct the two numbers from their XOR results because there are actually multiple possibilities. So constructing the numbers is not a good idea. If that is not a good idea, then how is this result going to help us? Okay, let us try to analyze this 6. Okay, so we have 3 as 0, 1, 1. This is 3. And then we have 5, which is 1, 0, 1. Okay, the answer 6 is 1, 1, 0. Now, if I ask you that what are the set bits in this number 6 signifying? Both these set bits, what are they signifying? Is there any information which is hidden in them about the two numbers? Is there any relation between the two numbers which is hidden in this number, which is encrypted in this number? Let us go back to the basics and see that we get a set bit in XOR if and only if both the operands are different. Right? A set bit in XOR means that both the operands that were given to it, which were fed to it, are different. One of them has to be set, one of them has to be unset. We don't know which one is set, which one is unset, but we know that they both are different. Correct? Now, if I know that using this 6, I can come to a conclusion that whichever are the two numbers which are occurring odd numbers of time, they are different. They are having different values for this bit position and this bit position. Does this make sense to everyone? You can actually try to also visualize this here, right? Both of them are having different values at this bit position. Wherever the final answer is having a 0, at that position, both the values are same in the two numbers. Okay. Now, can I use this information to solve the problem? I have got one information, which is the bit position at which the two numbers are different. Okay. So initially we had this complete array, which is 4, 1, 2, 3, 2, 1, 5, 4. Okay. The only information that I have is I don't know which number is occurring odd number of time, but the only information that I have is that the two numbers which are occurring odd numbers of time are different in the second and third bit position. One of them is going to have a 0, one of them is going to have a 1, right? If I divide all the numbers based on any of these bit positions, if I'm separating the arrays, if I'm making a partition in the array based on the position of this number, right? Can I say that both these numbers will always fall in different sets? If I'm trying to partition the array based on the bit position which is different in both the numbers, can I say that both the numbers will fall in different sets? No. I can say, right? Why I can't say that? Because I'm making sure that I'm partitioning based on a bit which is different in both of them, right? Let us actually convert all the numbers in their binary forms and let us try to perform the separation. So 4 is 1, 0, 0. Then we have 0, 0, 1, 0, 1, 0, 0, 1, 1, then 0, 1, 0, 6 is not there, right? 4 is there. So these are all the numbers, right? Now, if I am partitioning this array and I am saying that the final, if I take the XOR of all the numbers, right? If I am taking the XOR of the complete array A, what is the number that I'm getting? I'm getting 6, which is nothing but the XOR of the two numbers which are occurring odd numbers of time, right? And this 6 is nothing but, the 6 in binary is 110. I know that the two numbers A and B are different in both of these positions. So let us select any of these bits. Okay, let us select any of these bits and partition the array into two parts. So let us select the second bit position. Okay, now we are partitioning the array based on the value of this second bit. So we'll keep all the numbers which are having a set bit on in one side, and all the values which are having an unset bit at this position one side. Okay, so let us say here we are keeping all the numbers which have got set bit at this position. Okay, so 4 has not got a set bit, 2 has got a set bit, 3 has got a set bit, then 2 again has got a set bit, and that's it, right? And for all the numbers which have got an unset bit here, we have got 4, we have got 1, then we have got 1 again, then we have got 5, and we have got 4. Right? So if I'm separating all the numbers based on the bit position which is different in the two numbers, I can make sure that both the numbers are falling in two different sets. What about the other numbers? Can I say that in this set, in this half partitions, all the numbers are appearing even number of times except the one, and in this partition also all the numbers are going to appear even number of times uh, uh, except one or just one number? Yes. Does this make sense to everyone? What if we also have 5 in the array? We have 5 in the array, right? This we have 5, and 5 is falling here, right? If we have another 5, then we will need to have at least one number which is occurring odd number of times, right? Currently we have 5 and 3 which are occurring odd numbers of times. So what we have done is we are partitioning the array based on a digit which is different in both of them. If that is the case, that we are partitioning the array based on a different digit, then we can make sure that these two numbers will always fall in different sets. And now if you observe, we have reduced this to the previous problem that we have solved, right? In this part, all the numbers occur even number of times except one. In this part also all the numbers occur even number of time except one. Okay, so what we have to do, take the XOR of all these numbers, take the XOR of all these numbers. What will be the XOR of all these numbers? The XOR of all these numbers will give you 3. The XOR of all these numbers is going to give you 5. Is this whole thing clear to everyone? So we partition based on one singular bit rather than for each set bit. Correct, Bhavya, that is absolutely correct. We are selecting any of the set bits. So currently in this case, I have partition based on the second bit. You can also do the partition based on the other set bits, because set bit will guarantee that a set bit in a XOR result is going to guarantee that the two numbers are different at that place. If the two numbers are different at that place, they will definitely fall into different sets, and all the other numbers are occurring even number of times. So if the other numbers are having a set bit, they come with all their copies, right? So if 2 is coming here, 2 will not come alone, 2 will also bring the other 2, so all the numbers will come even number of times. Okay, how to find which bit is set? Okay, we have solved the first question that we have solved. Can you not use that thing? You know how to check whether the ith bit of a number is set or not, right? You can just loop from 0 to 32, assuming that there are 32 bits that your data type is being used to store. So you can just loop from 0 to 32. The first bit that you are finding that is set, you can do the partition based on that. Okay. So this is going to give you which bit is set. Okay. Now the question is, do you need any extra space for this? Is some extra space required here? If there are n odd occurring number, then this will not work. This only works if there are two numbers which are occurring odd number of times. Okay. Do we require some extra space? Let us try to see the code. Okay. So let us say that we have a XOR which we initialize from 0. Okay. And we are calculating the XOR of all the array elements in this variable. Okay, so we'll just say XOR is equal to XOR A of I. Okay, so what will this XOR hold? This XOR is going to hold the XOR of the two numbers that are occurring odd numbers of time. Okay, now what we can do is we can first find out a position. Okay, so first find out a position at which you have a set bit in this XOR. Okay, how to find out that position? To do that, if we are assuming that we are dealing with integers are stored in 32 bits, right? So we'll be running a loop. So let us say that we have a position variable which we are initializing from 0. Okay, and then we are saying that for all the values of this position, all the values that the position can take, which is going from 0 to 32, okay, we can say that check the exact same thing that we had done to check whether the ith bit is set or not. So we'll be taking XOR here and one left shifted by I bits, right? So here we can say if XOR and one left shifted by I, okay, if this whole thing is greater than 0, this means that this number XOR is having a set bit at the ith position, right? So we can just set the value of position by I, and we don't require any other set bit now. This is enough, so we can break. We just require whichever is the first set bit. Okay. Now what all we have? We have the XOR, and we also have a set bit in XOR. We have a position of one of the set bit. Okay. If two numbers we got in the same set. Okay. Yes. Can you please use some other names? Maybe this sounds very derogatory if I use your name, but you fool. How can they fall in same set? If you are partitioning the array based on a bit position, which is different in them. If you are already selecting a quality which is different in both of them, how can they fall in same set? For example, let us say that you have got a bunch of books. Some of them have got black cover, some of them have got white cover, and you are the property that you are selecting to partitioning is the color of the book. So you are saying that I will keep all the black books here, all the white books here. Can the two black and white fall in same set? No, right? They cannot. If you are selecting a property which is already different in them, right? Then they will never fall in the same set, right? So what happens till now? Till now we have the XOR, and we also know a position at which the XOR has a set bit. Okay. Now the XOR has a set bit in this position. Now the next step is that we have to divide all these numbers based on this set bit. So how can we do that? And we have to divide all these numbers without actually using some extra space, right? So now do you guys remember the problem that we had just discussed before this problem? Given an array, find the XOR of all the numbers where ith bit is set. This is the exact same problem that we have to solve inside this problem. You have to find the XOR of all these numbers where the bit at this position is set. Okay, so how can we do that? We can initialize two numbers. So basically we have to find the XORs of all the numbers where the bit is set, and parallelly we also have to find the XOR of all the numbers where this bit is not set, right? So we can say initialize, let's say num1 and num2 with 0, and then we can start the loop from I equals to 0 and then I less than n, I plus, and then we can say that if a of I, and again we are checking the exact same thing. We are just checking whether the whether this number, whether the array number has got a set bit at this position or not. So I shifted by positions. If this is greater than 0, if this is greater than 0, this means that the number has got a set bit here. So keep the XOR in num1. Else, what can we do? Else we can say num2 is equal to num2 XOR a of I. Okay, now does this make sense? So all the questions, all the concepts that we have studied in the throughout the class have been used in this single problem, right? Let us quickly revise this problem. The problem was that you are given an array where all the numbers are appearing even number of times except two elements, right? So what we did was, first thing was that we took the XOR of all the numbers. Taking the XOR of all the numbers gave us the XOR of the two numbers that are appearing odd number of time. Okay. Once we get the XOR of all the XOR of the two numbers that are appearing odd number of time, this XOR gives us the information about at which bit position the two numbers are different. Now, if you know that in at this position where the XOR is having one of the number definitely is going to have a 0, the other number will definitely have 1. They cannot have same value, right? So now partition the set, partition the whole array with respect to this position. So this number which has a 1 here will go to one side. This number which has 0 will go to the other side. And all the numbers, since are appearing even number of time, they will, whether they go to the set 1 or set 2, they will go with all their copies. So now we have reduced this to the previous problem where all the numbers were appearing even number of time except one number, right? So now we just have to calculate the XOR of the two sides. Okay. Now the question is for 3-7 it was filled. Okay, Sai, if that is your input, that is a wrong input, because if you haven't, I think you haven't understood the question correctly. The question says that all numbers appear even number of times, right? So there has to be a bunch of numbers which are appearing even number of times. Then there has to be exactly two numbers which are appearing odd number of times. This is the question. Okay. Now you cannot change the language of the question and expect the same approach to work, right? Right. This has to be correct. This is Ankur. Thanks for correcting. This is not I. This has to be one left shifted by position. Thanks for that. Right, because we are just checking whether the bit in this position is set bit or not. Okay. Okay, guys, Kuldeep has declared that he has solved all the problems even before the class has ended. We'll just check that, Kuldeep, and If that is true, you will be the winner of today's contest, right? Okay, so I will now end the session. Thank you, guys. Please do solve all the problems. Tomorrow we'll be discussing some more interesting problems on bit manipulation. Okay. Thank you, everyone. Good night. Okay, so I will just share my screen. Just give me a moment. Okay, so first of all, today's winner, everyone, please congratulate Srinivas Rao. Srinivas is the guy who solved all the problems in the minimum amount of time. He was the first person to solve all the problems which were given in the last assignment. Okay, everyone, please congratulate Srinivas for this. Videos downloadable. Is there a feature in YouTube for that? Can we like, I'm not aware of that, but if there is a feature to make a video downloadable, we will do this. Otherwise, the video is always available on YouTube, so maybe you can use the feature of YouTube offline and save the video, right? Okay, so there was a problem in the assignment which I can see has been solved by very few students, right? So we'll discuss that problem because that is also a very important problem with respect to the interviews. Okay, the problem says that you're given an array and you have to find the pair that has got the minimum XOR. So out of all the numbers in the array, you have to find the pair of numbers which has got the minimum XOR. Did you guys attempt this problem in the assignment? So for example, if you have 1, 4, 5, 2, 3, if this is your array, you have to find the pair that has got the minimum solve. Okay, so now all of you who have already solved this problem, can you guys quickly tell me what is the best way to do this? In this case, the minimum XOR is going to be between 2 and 3, okay, which is going to be 1. Thank you, Hemant. Thank you for your appreciation. So you have to find the pair that has got the minimum XOR. Okay. Okay. SK Creations is saying that maintain a map with bit count of all the numbers. Okay. Uh, any other approach? Right. Sai, that is a correct observation. Okay. Now some of you are saying that sort the array first. Okay. Why does sorting help here? What is the reason like most of all of you who have solved the problem have used sorting for solving this problem, right? But why sorting actually helps in this case? XOR of 4 and 5 is also 1, correct? So that can also be an answer, but you have to return this value. So this value remains same in both the cases, right? So answer here is going to be 1. Okay. So let us say that you have to find the minimum, or let's say that you can return any of the available answers. So any of these two will be the answer. Okay, let us not return the value, let us return the pair. So any of these two will be the answer. Minimum elements XOR is minimum. Is that the case in this case? You can have the XOR of even the maximum elements is also minimum, right? XOR of 5 and 4 is also 1. XOR of 2 and 3 is also 1. But the minimum element here is 1, and 1 is not giving the minimum XOR with any of the elements, right? Okay, now to solve this question, we need to use a very, very important property of XOR, and then we'll make some observations. Okay, so a very important property of XOR that we studied in the last class, that if you are given a number A, then the XOR of A with A is going to be 0. Is everyone clear with this thing? XOR of A and A is always going to be 0, which means that if I have got a number which is repeating in this array, can I say that the minimum XOR will always be 0? If I have an array which has, let's say, which has a pair where the numbers are repeating. So if this is the array, what should be the answer? If this is the array, answer would be 4, 4, because this will always return 0, and we cannot have a XOR which is less than 0 if all the numbers are positive, right? So if I can find a number which is repeating in the array, then the answer is always 0, right? But what if there is no such number which is repeating? Let us again try to observe why this XOR is 0. Why the XOR of a number with itself is 0? It is 0 because at all the bit places, the value of digits in both the numbers is exactly the same, right? If I have 4 XOR 4, in all the bit places, this place, since both the numbers are exactly the same, these values are also same, right? That is why we are getting 0, 0, 0 at all the bit places. Okay, now just use this thing, and can you say, by just looking at this, that if the number are closer to each other, if the number are numerically closer to each other, then chances of having a lesser XOR will be maximized. The closer the numbers, the lesser would be their XOR. For example, if I'm taking XOR of 4 with 5 and versus XOR of 4 with, let's say, 16, this pair is going to give me a lesser XOR versus this pair. Does this observation make sense to everyone? Because chances of finding same bits are going to be lesser in the are going to be more in this case versus this case, right? Okay, now can I also say that since I want a value which is smaller in magnitude, right, which is smaller in the value, the most significant digit always decides what is going to be the actual value, right? Because if or the most significant bit is the one that decides whether the value is going to be larger or smaller than the other value, right? For example, if I have 4, right, and I have 8, the most significant digit which is set in 8 is here. The most significant digit which is set in 4 is here. The number which has got the most significant bit set on as left as possible is always going to be a number of higher magnitude, right? Because this is the bit with the highest power of 2, right? So to actually get a minimum XOR, we want to minimize the value of the most significant bit, correct? So we always want that the first set bit from left should come as late as possible, since we want to minimize this value, right? So the first set bit should be on as right as possible in the result. Does this observation make sense to everyone? So ideally, if I am given if I'm given a list of number, and if I select a number out of that list, and I want to find out what is the minimum XOR of that number with any of the given number, right? So if, let's say, I'm given a list of these numbers, and I select any random number, and I want to find out what is the minimum XOR involving this number, which number is going to give me the minimum XOR with this number b. Okay, so let us say that b has got this as the binary representation. Now a number which has the exact same binary representation, which means that if I have b again in this array, then this definitely is going to give the minimum XOR. But if b is not present, the next choice, what should be the next choice? The next choice would be that if I have a number which has just this bit as different, all the other bits should be same, right? This is the best choice that I can have if I don't have b again in the array, right? So in this case, the XOR is going to be 1. What is the other best choice that can I have? That what is the next choice? Next choice would be that the first different bit occurs here, right? Or if that is also not present, then I would say that the first different bit should occur here, and so on. So I want the first different bit to occur as right as possible. The first different bit with this number, if I have a number which has got which is different with b, different from b, and the different bit is occurring as right as possible, then that number is going to give me the minimum XOR, right? Out of all these numbers, whichever number is having the different bit on the rightmost side is going to give me the minimum XOR. Does this make sense? For example, if I list down some numbers, let us say I have 11100101, then I have 11000100, and then I have 11110001, then I have, let us say, 10001111, and then I have 11001110. Okay, now out of all these numbers, which number do you think is going to give the minimum XOR with this given number b? Let us try to analyze which number is having the different bit on as right as possible, right? So if you analyze this number, the different bit occurs here. Here we have 0 here, and in this number we have got 1, right? In this number, the second number, the different bit occurs here. You have 1 in the original number, you have 0 here. In the next number, the different bit occurs here again, right? In the next number, the different bit occurs here. In the next number, the different bit occurs at this position. Which of all these numbers is going to give the minimum XOR with the number? The last one, correct? Because here the different bit is occurring on as right as possible, right? If you take XOR of the first number, the result will be having the third bit in the result from left is going to be a set bit, so the magnitude will be very high. Here the fourth bit from right is going to be the this is going to be the set bit in the result, right? So again, the magnitude is going to be higher with as compared to this number. If you take a XOR with this number, all these bits in the result are going to be 0 because all of them are exactly same as the original number. This is the first bit which is different. That is why this is going to give you a set bit. Okay, so this is the idea behind this approach, right? You have to make sure that you are taking the XOR of a number with that number which has got the first different bit on as right as possible. Okay, now how can we do this? So intuitively, this comes to the mind that since all the bits from left to right should be same, right? Should be we want the maximum similarity between the numbers. So now the closer the numbers, the more chances we are going to have in the similarities of the bits, right? The more close the numbers, uh, the the farther we'll find the different bit, correct? Okay, so Himanshu has an observation: minimum difference between two number will give the minimum OR. Is that correct? Now there can also be a contradiction to this. For example, you have numbers like 8, 10, and let's say 7. Okay, what is the minimum difference between these three numbers that we can have? We have 8, 10, and 7. 8 is 100, 10 is 1010, and 7 is 111. If you are just checking the minimum difference, then you will be selecting 8 and 7. What is the XOR between 8 and 7? The XOR between 8 and 7 is going to be very large, right? This is going to be 15. So this observation can have some exceptions, right? But the observation that we made, earlier is that we want all the digits. We'll be checking for each and every number, and for each and every number we'll be considering the XOR. We'll be considering the XOR with that number which has got the first different bit as right as possible. Okay. So if you are considering the XOR with 8, you have got two prospects, right? Which of these two has got the first different bit as right, more on the right side? 7 has got a first different bit on the first bit itself, so 7 is not the contender with 8. Okay, 10 has got two similar bits, so 10 is a contender with 8. If you take XOR of 8 and 10, then you will be getting 2, right? So 8 will be giving the minimum XOR with 10. Then you will be checking what is the minimum XOR involving 10. So again, for 10 as well, 8 is going to be the prospect pair, and for 7 also 8 is going to be the prospect pair, right? And then the XOR of the minimum XOR involving 7 is going to be 15, but we will select whatever is the minimum out of all the pairs, right? Now if this thing is failing here, that the minimum difference is not giving the minimum XOR, then how is sorting helping here, right? So if you are clear with this observation, right, if you are clear with this observation, XOR of any two consecutive numbers after 1 and 2 always gives us 1. No, Tuhina, I just gave you an example, right? 8 and 7 are consecutive numbers and they are not giving 1. This is not 1, this is 15, right? So the observation that you are making can be correct only in those cases where you are not incrementing, you are not adding a new digit, right? So if you are switching from a number which is of the form 2 raised to power n minus 1 to 2 raised to power n or 2 raised to power x, in that case you will be getting a very large XOR value. Okay. Okay, so how to solve this problem? Now, the intuition that comes to the mind is the closer the number, the more similar bits we are going to get on the left hand side. Okay, if you sort all the numbers, if you just sort these numbers, you get 7, 8, and 10. Right? The intuition is the closer the numbers, the lesser the XOR. However, we have seen an exception of this, right? But if you sort these numbers, now I can say that 8 will either give a minimum XOR with 7 or 8 will either give the minimum XOR with 10. So these two are the only numbers with which 8 can give the minimum XOR. Let us say that we had more numbers in the array if you also add 5, 3, 12, and 15, if you have all these numbers, even then I can definitely say that the XOR that 8 is giving with 7 is always going to be smaller than the XOR that 8 gives with all these numbers. And the XOR that 8 gives with 10 is going to be smaller than the XOR which 8 is going to give with all these numbers. So 8 is always and always going to give the minimum XOR either with 7 or with 10. Okay, does this make sense to everyone? Because out of these two, one of them is going to have the maximum number of similar bits on the left side. Okay, that is why if you sort all the numbers, and you just check the XOR of all possible pairs, you will be getting the minimum XOR out of all the possible pairs. Because 8 can only give the minimum XOR that involving 8, the minimum XOR that which you are going to get involving 8 is going to come either from 7 or from 10. It will not come from these numbers. Why? Because these two are the closest to 8. This one is the closest on the left hand side, this one is the closest on the right hand side. And we have seen that to get the minimum XOR, we want all the digits on the left hand side similar to the given number, right? Is it clear now? How 7 and okay, 7 and 8 are not giving the minimum XOR. Try to understand this thing. How are you actually going to find the minimum XOR? Think about the brute force approach. The brute force approach would be, if you don't just skip all these things which we have discussed till now. What is the brute force approach of doing this? The brute force approach is that for every number you take XOR with each and every other number, right? And you store that in a variable minimum. If you find the minimum XOR, then you store that in a variable. This is going to cost you order n square time, because for every number you are going to take the XOR with every other number, right? This is going to be an n square approach. Now what I am saying is that you don't need to take XOR of 3 with each and every other number. You can only take the XOR of 3 with two numbers, one which is closest on the left side, one which is closest on the right side, and the minimum of that two is going to be the minimum XOR that 3 can give you. Okay, so in this case, if you are looking for what is the minimum XOR involving 8, right? What is the minimum XOR involving 8? If you want to find that out, if you are doing a brute force approach, you will be checking 8 XOR 3, 8 XOR 5, 8 XOR 7, 8 XOR 10, 8 XOR 12, 8 XOR 15, each and every number, right? But I'm saying that you don't need to do all of these things. These all calculations are totally needless. Why? Because we have seen that if the number of bits are similar on the left side, right? I want to find the number which has got a different bit on as right as possible. I can say by intuition that the closest number are going to give me that. So 8 XOR 3 will always be greater than 8 XOR 7, because 7 is closer than 3, right? Similarly, I can say that 8 XOR 10 will always be minimum than 8 XOR 12. Okay, because again 10 is closer to 8 than 12. So chances of having different bit is going to be more on right side for 10 rather than 12, right? So this is the intuition behind this, that you sort the numbers and then you just check for every number, you just check with the adjacent numbers. So for 5 you will be checking with 3 and 7, for 7 you will be checking with 5 and 8, for 8 you will be checking with 7 and 10, and so on. Okay, is this clear to everyone now? Or should we also try to prove this mathematically? Okay, if you are not convinced with the intuition, let us try to see a mathematical proof behind this. Okay. So let us say that we have got two values A and B. Okay. And I'm saying that A is smaller than B. Okay. If A is smaller than B, then there are some bits for which the value is same in A and B. And then this is the first bit with in which the value is different in A and B. Okay. If A is smaller than B, and this is the first position where the bits are different, what can I say about the values? Can I say that A will always have 0 and B will always have 1? Yes, no, right? Because A is less than B, and this is the first bit at which A and B are different. All these are exactly the same, whatever be the value. This is the first bit where these two numbers are different, right? So I will, so we can definitely say that A is going to have a 0, B is going to have a 1. Okay. Now, if you put another value between these two, okay, if there is another value between A and B, let us call it X. So A and B are not consecutive, but A and B are just two values in the array. And now we insert a value X here, okay. And X has got a value between A and B, okay. So I can say that A is less than X, which is less than B. This is the relation, okay. What can we say about this bit in X? Is it going to be 0 or 1? It can be anything, right? It can be 0, it can also be 1. X, this bit can be anything, right? It can be 0, it can also be 1, right? Because these bits are same in A and B, we are not sure about what is there in these places in X, right? So X can have a 0 here, X can also have a 1 here, right? Now let us consider both the cases. Let us consider a case where X has got uh, a 0 in this place, and the other case where X has got a 1 in this place. Okay. Now, if I take XOR of all the pairs out of these three numbers, which one do you think is going to be the lowest? Which one out of these three pairs is going to be lowest? Can I say that the XOR of A and X will always be lower than the XOR of X and B and the XOR of A and B? Yes, because A and X have got 0, 0 here. So the first different bit is going to be after this, right? Correct. So this is going to be the smallest. If X has a value 1 in this case, then can I say that X XOR B is always going to be less than A XOR X and X and A XOR B? Yes, because in this case these two are going to have the same bit at this position and rest all the bits are same, right? So they will have the first different bit on more left right side, correct? So in any case, whether X has got 0 or X has got 1, we can see that we are always finding the minimum XOR between the adjacent pairs, between the closest pairs, right? Is this clear now? So now we can say with a proof that the closest XOR or the minimum XOR occurs between the closest element. So if you have got an array, you can just sort the array and you can just check the XOR of the consecutive numbers. Okay. Should we move to the next problem now? Okay, let us now try to solve a problem which was asked in Google Code Jam. Okay. So the problem says that you are given a distributed system. This was asked in Google Code Jam 19. Okay. The problem says that you are given a distributed system where you have a master server. Okay. And this master has got multiple slaves. Are you guys familiar with the master slave architecture? If you are not, I would recommend all of you to go and read about what is master slave architecture. Okay. So you have got this system where there is a master server and there are slave servers, but the job that is given to these servers is very trivial. You are entering a binary string in the master server. Okay, a random binary string is entered in the master server, and since the master server, this is a server which cannot store the things. So what it does, it sends one bit to every slave server. Okay, so if let's say if there are 4 slave servers, okay, so if you have one master server and then you have got 4 slave servers, so then in that case you will be entering a binary string of length 4. Okay, and the master server, it distributes each and every bit to one server. So 1 goes here, 0 goes here, 1 goes here, and 1 goes here. Then after a while, master server asks all the servers to return these values so that it can return the string to the user. So S1 returns 1, S2 returns 0, S3 returns 1, S4 returns 1. Okay. Now, the problem here is some of the slaves are faulty. Some of the slaves are not working properly. So let us assume that if S2 is a faulty slave, it is not working properly. In that case, S2 will not be able to return this bit. So S2 will not return anything. Okay, S2 is not getting the instructions to return, so it will not return anything. So if S2 is faulty, when master asks for the string, he will only be getting 1 1 1 because 0 is gone now. Okay. If S2 and S3 is also faulty, in that case you will only be returning 1 and 1. Okay. If S3 and S4 are good, but S1 and S2 are faulty, in that case also you will be getting 1 and 1. Okay. So any server, which server is faulty, is not going to return anything. Is the problem clear to everyone? Or is the scenario clear to everyone? You have a master server and you are just inputting a binary string of length n, where n is the number of slave servers that you have. Master server distributes each and every bit in the exact same order to all the slave servers and then asks for the bits to create the string again. Okay. So if the slave servers are faulty, they do not return anything. Okay. You have to identify, given the number of slave servers, you have to identify which of these servers are faulty servers. Okay, you are only given the number of slave servers. Identify the faulty servers. Is the problem clear? will we be given the final string? Yes. So what you are given is that you can input any string. You can input a string of length n. So let us say that you are given two functions, read and write. Okay. This is a function write, which takes a string, a binary string of length n, and you have got a function read, which returns a binary string. The length can be less than or equal to n. So here the length should be exactly equal to n. Here the length will be less than or equal to n based on how many servers are faulty. Let us take an example. So let us say that number of slaves is 4. Okay. And out of them, so you have got 4 slaves, and out of them slave 4 is the faulty slave. This is the, so this is not given to you. You are only given that there are 4 slaves, and these two functions are given to you. Using these two functions, you have to identify which slave is the faulty slave. Okay. So if you enter a string, you just say write 1101. If this is the string that you enter, and after this, if you call read, right? If you call read, then the string that you get is 110, because slave 4 is faulty and this one will not be returned. Okay. If again you call write 1100, in this case, if you do read, you will be getting 110, because slave 4 is faulty, so you don't get this. Okay. Any number of slaves can be faulty. There is this is not given that only one slave is faulty. Any number of slaves can be faulty. It might be possible that slave 3 and slave 4 both are faulty. In that case, you won't be getting the last two bits of your string. Okay. This is multiple answer question. No, Akshay, this is not a multiple answer question. This is actually supposed to be a coding question. This in Google Code, then you are supposed to code this question. Okay, Deval, that is in the right direction. What is the time complexity of your approach? At least one slave will be working. It might be possible that all the slaves are faulty, although you will get to know that in the first read call itself, but it is possible that all the slaves are also faulty. If they are faulty, they never return anything. Okay. We need to return number of faulty slaves or name. No, you have to return the names, because number is definitely clear in the first call itself, right? You can just subtract the length of the output from the length of the input, right? So number is clear in the first call. You have to return the names of all the faulty slaves. Okay, Deval, that is correct. Can you optimize that? Okay, now the question is, can we compare the bits and check the missing one? Okay, let us take a bigger example. Okay, if this is, if we are talking about only 4 slaves, then this looks kind of obvious, right? If there are 100 slaves, and you are sending a string of size 100, okay? And in the output, let us say you are getting a string of size 81. So this has got 100 length, okay, and in the output you are getting a string of size 81. How do you recognize which all 19 slaves are faulty? Because they can be the first 19, they can be the last 19, or they can be the 19 in between. How do you compare? You have got a string of length 100, you have got another string of length 81. how do you compare these two strings? Are you comparing this one with this one and you are saying that the first slave is correct? It might be possible that this first slave is not correct, right? Let us take another example. Let us say that you input all 1. Okay, if the input is all 1 and you send 100 ones, and then you are returning, you are getting in return 81 ones. These are 100 ones, and then in return you are getting 81 ones. How do you find which 19 slaves are not working? Take XOR of the return string with the original string. What will that return? So Preeti, are you getting the problem in the first place? The problem is that you have to you don't have to identify the count of the faulty slaves. You have to identify the names, right? You have to tell that S1 is faulty or S4 is faulty. Now, if you are comparing and you are saying that this one is correct, which means S1 is not faulty, it might be possible that at S1 was faulty and this input has this output is from S2 or S3 or S4. Yes, an image that is in the right direction. It is correct. That can be one of the solution. Okay, what could be the brute force solution here? Can you guys suggest a brute force solution? Devil has already suggested. You have got n slaves, okay? And you don't know how many of them or which of all these slaves are faulty. The brute force solution is check each and every slave one by one. If you input this string, right, where you have a single bit as a set bit and then all other as unset, and then if you input this, you know that the set bit is going to the first slave. This bit should be stored in the first slave. All the other bits are 0. When you read, you just have to make sure whether there is one bit set in the output or not, right? So you write this number where you have 1 and then rest all n zeros, okay? And then you do a read. If read returns a binary string of any length which has at least one bit set, can I say that S1 is not faulty? Or if read returns a string which has got all 0, can I say that S1 is faulty? Yes, because I am sending only one set bit which should go to S1, and when I do the read, it should be written from S1. If I'm not getting any set bit, this means that S1 definitely is faulty because there was only and only one set bit in this, right? Battery 12%. I think that is sufficient. 12% battery is okay. Okay. What if we send all 0 bits? Srinivas, you will not gain anything from that, right? If you are sending all 0 bits, there is no identifier, and then you return, then you get, let's say, 3 0 bits in return. What do you gain? You don't gain anything, right? You only know that there are 2 bits which are slaves which are faulty, but you don't know which one. But if you are sending this string, and in return, let's say you are getting three unset bits, one thing you know for sure is that S1 definitely is faulty because there has to be at least one set bit in the output if S1 is not faulty. So this If you send this string, you can make a decision whether S1 is faulty or not. Okay. Similarly, if you send another string of the same kind, so this is just to check whether S1 is faulty or not. Similarly, to check S2, you can set the second bit and keep all the remaining bits as unset, and then this will check whether S2 is faulty or not, because in the return in the output that you are getting, if there is no bit which is set, then you are sure that S1 is faulty, because the only set bit was sent to S2, and if it is not getting returned, then S2 definitely is faulty, right? Similarly, if you want to check S3, you can set a set bit in the third position. If you don't get the third bit as set, you can definitely say that S3 is faulty. Now, does this make sense to everyone? Correct. Yes, Suji, that is totally correct. How many queries we will have to do? What is the total number of queries if you are going to go by this approach? Or what is the time complexity? For every server, for every slave server, we are doing a different query, right? For every slave server, I'm trying a different string, which means that for every slave server, I will have to do a query. So I will be doing exactly n queries. So time complexity becomes order n. Okay, correct. N is the number of slaves, correct. Now, can we optimize this thing? Can we do this in less than n queries? Okay, now some of you have got some optimizations. Some of you are saying that let us set 2 bits one, and now you can just check whether the first is set or the last is set. Based on this, you can decide on 2 servers at once, right? This might also work. You can actually every query can give you output about 2 servers. But let's say if there are only 2 servers, S1 and S2, and if you give this as the input and you are getting 1 in the result, how do you know whether S1 is faulty or S2 is faulty? So this again is going to have some edge cases which you will have to deal, right? Okay, now guys, if let us say that some servers are faulty, right? Let us say that we have got 4 servers, or let's say we have got 5 servers. We'll make a very interesting observation here. Okay, if we have got 5 servers, out of which S2 and S4 are faulty, these 2 are the faulty servers, rest all are correct. Okay, these 2 are the faulty servers. Now if I am writing a string 11111, what is the output that I'm going to get? Can you guys quickly write outputs with me? The output that we are going to get is S2 and S4. These 2 will be missed out. So the output that we get is 111. Okay. Then if I enter another number, let's say 10101, what is the output that we are going to get? We are going to get 111. If I add another number, if I input, let's say 10000, what is the output that we are going to get? We get 1 and then 00, right? If I enter 00111, what is the output that we get? We get 0 and then 1 and then 1. Are you able to observe one thing, that in all these input, since S2 is faulty, this whole column is missing from the output, right? The first column is present as it is, right? 1110, this column is present as it is. Second column is completely missing. Third column is again present as it is. Fourth column again is completely missing. So we have got two voids in the output, right? Rest everything is totally correct. First column is totally matching. Second is totally gone. Third is matching. And then fourth is gone. Fifth is also matching. Correct? Can I use this column to uniquely identify a server? Vignesh, that is also a correct approach. Using binary search will also solve this problem, right? So can we use this column which is missing to uniquely identify a server? What if I create a pattern in such a way that this column is representing a number? Okay, because this is my input and this is my output. Okay, if I can somehow make sure that this whole column is meaning something, this is giving this is, if let's say this becomes a unique identifier, this is representing the ID of that slave, right? So for example, if I number these slaves from 0 to 4, okay, and now I just give in input, I give the input such that the first column is always going to have all 0 values. Okay, then the second column is always going to have values in this order. The third column is going to have values like this, and the fourth column is going to have values like this, and then the fifth column is going to have values like this. Okay, if I send the input in this order, right, what will be the output? If I'm sending the input in this order and slave S3, S2 and S4 are empty, this is the first string. The output that I get is 0, 0, 0. Then in the next one, the output that I get is 0, 0, 1. Then the next output is 0, 1, 0. And then the next output is 0, 0, 0, right? Again, this whole column is missing from here. And this whole column is also missing from here, right? What does this number represents? What is this number in decimal? If you consider this first column as a binary string, what is the representation of this number in decimal? This is nothing but 0. What is the representation of this number in decimal? This is nothing but 1. What is the representation of this number? This is again nothing but 2. This is 3. This is 4. Okay. In the output, what are you getting? In the output, you are getting the first column, which is representing 0, which means slave 0 is totally fine, right? We had sent all these strings in a way that each and every column is making a pattern which can be used to uniquely identify all the slaves. If I'm sending all zeros in the first column, this means that this is for slave number 0, right? Then I am using the second column to uniquely identify the first slave. I am using the third column to uniquely identify the second slave. If a column is missing, I know that a number is missing. So I have 0 here, I have 2 here. This column is representing 2. I don't have 1 here, right? I don't have 3 here. I then have 4. So now I can say that the slave which is numbered as 1 and the slave which is numbered as 3, the 1 and 3, they both are faulty. Does this make sense to everyone? So we are using the bits to uniquely identify the numbers, and we are actually creating a mask of these bits, right? If two columns have same numbers, is that possible? Will two columns ever have same numbers? Can you have two numbers which have the exact same binary representation? Can you have two numbers which can have exact same binary representation? No, that is not possible, right? So no two columns are going to have same value. Okay. Now the question is, how many queries we'll have to do? If you go by this approach, how many queries are required? Just pay attention that these are not the queries. This is one query. This is the other query. This is the third query. This is the fourth query. How many queries are required? In this case, to get how many queries are required, just again observe what we are essentially doing. We are representing each and every slave in binary form, right? So the length of the query is equal to the number of slaves, but the number of queries that we are making is equal to the number of bits which are required to represent these numbers in binary, right? How many bits do we require to represent a number n in binary? How many bits are required to represent a number n in binary? Exactly log base 2 n bits. So how many queries do we need to send now? We need to send exactly log base 2 n queries. Okay, if there are 1,000 slaves, how many queries do we need? If there are 1,000 slaves, what is the number of bits in which we can represent 1,000? We can represent thousands inside 32 bits, right? So you don't need to send more than 32 queries. In the initial approach, we were sending n queries. That means for 1,000 bits you were querying it how many times? Sorry, for 1,000 bits you can actually do it in 10 digits, right? 2 raised to power 10 is your 1024. So any number less than equal to 1024 can be represented in 10 bits. So if you have got 1,000 slaves, then you can do it. You can find the faulty slaves only using 10 queries. In the initial approach, you were doing 1,000 queries, right? Okay. So does this thing make sense to everyone? Now there is another approach to solve the same problem which some of you have already written in the comment section. You can also solve this using binary search. Okay, we can maybe reiterate over this when we do binary search classes. But I would recommend you guys to think about that. Okay, you can maybe have this type of a pattern where you separate ones and zero, and now you can count how many faulty slaves are present in the first half, how many faulty slaves are present in the second half, and then you can do the exact same thing in the first half, and then you can do the exact same thing in the second half, and you can again find out how many faulty slaves are there. Okay, so that is another approach using binary search. You can try to think about that approach yourself. But is this thing clear? Okay. Pseudocode. Did you get the idea, Shubha? If you get the idea, you can just Google this problem. You can Google, or maybe we can post the link in the chat group. The problem where it was asked in Google Code Jam, and then you can attempt it there. Okay. Thanks a lot, Himanshu. Thanks a lot, guys. Okay, so now I will end the session. Tomorrow onwards, we'll be starting lectures on, no, tomorrow we'll be having a lecture on 2 pointers, problems based on 2 pointers. And then after that, we'll be doing classes on searching. Okay, so I hope you learned something in today's lecture. The last 1 hour was useful for you. If you find it useful, please do like the video. And if you want any topic to be covered, please write that in the comment section. Okay. Thank you guys. Thanks a lot. Good night.